In 1589, Galileo famously dropped two cannonballs, a heavy one and a lighter one, from the Leaning Tower of Pisa to show that they would hit the ground at the same time. But it's not clear that he actually really performed this experiment. We do know that Apollo 15 astronaut David Scott performed a similar demonstration on the moon using a hammer and a feather. We have just conducted an extreme version of this experiment, using a super dense neutron star and a white dwarf instead of hammers, feathers, or cannonballs. The target of all this experimenting is the strong equivalence principle, gravity's remarkable compensation scheme. The heavier an object, the stronger the force of gravity. But at the same time, the heavier an object, the more force you need to change its speed. These two effects cancel each other out. So, when falling, a heavy object like a whale accelerates in exactly the same way as a light object like a bowl of petunias. In the words of Einstein, gravitational mass is inertial mass. In his general relativity, since all objects fall exactly the same way, gravity is geometry rather than forces. The Earth is following the straightest path it can through warped spacetime, round and round the Sun. But this only works if objects all actually fall the same way. If this equivalence principle is wrong, then Einstein's whole idea of gravity as geometry goes out the window. So far, it doesn't seem to be wrong. Over decades, laser ranging measurements using mirrors that David Scott and colleagues left on the moon have tested the principle for the gravity of the Earth, the moon, and the Sun. But what happens when the objects have much stronger gravity? In Einstein's theory, gravity itself has mass, which will in turn generate more gravity. Will the compensation scheme still work? This extra self-gravity is noticeable in extremely compact objects like neutron stars or black holes, which warp spacetime strongly. So we looked at one of those. PSR J0337 plus 1715 is a triple star system at 4,200 light-years distance from the Earth in the constellation of Taurus. At the center of this system is an odd couple. One is a neutron star, which has the mass of 1.44 suns crammed into a sphere the size of Amsterdam. The other is a white dwarf, a small star 1/5 the mass of our Sun. They circle around each other every 1.5 days. The super-dense neutron star and the far less extreme white dwarf provide just the contrast we need to test the equivalence principle. What's more, the neutron star provides a very handy and precise timekeeping mechanism. It rotates 366 times per second, and beams of radio waves rotate along. They sweep over the Earth at regular intervals like a cosmic lighthouse. We can pick up the radio pulses, which are so fast they sound like a tone, and use them to track the neutron star. When it moves towards us, the distance to Earth becomes a bit shorter, and the pulses will arrive seconds earlier. When it moves away, the pulses will arrive later. On top of that, our odd couple is falling freely in the gravity field of a third star, a white dwarf at some distance. If the inertial mass and the gravitational mass of the super-dense neutron star were different, it would accelerate differently from the inner white dwarf. This difference would shift their orbits off-center, which would look like a wobble in our measurements. So, we measured the arrival times of 27,194 of these pulses to the nearest microsecond. We recorded over 1,200 hours of observation spanning 6 years using 3 radio telescopes: the Arecibo radio telescope in Puerto Rico, the Green Bank telescope in West Virginia, and the Westerbork radio telescope in the Netherlands. Using a computer simulation of the triple star system, we found there is no wobble, with a margin of error of only 30 meters. So, Einstein's general relativity passes the test with flying colors, while a large range of alternative theories are now ruled out, including some versions of string theory. Even an object with one of the most warped spacetimes in the universe falls exactly the same way that Galileo's cannonballs did. Or didn't.